Let us now see binary search based solution for this problem. This is one special problem where our input is not sorted and we are using binary search. Let's see how do we apply binary search here. So let's do a quick recap of the question. We are given a set of books and every book has 13 pages, and we are given a number of students. In this example, we are given 2 students and we are given 4 books. We need to make sure that books are assigned to these students in such a way that the maximum number of pages read by a student is minimized, and with the constraint that a student can only read contiguous set of books, right? If a student is reading 10 and this 10, then the student must read 20 also, right? Can't skip a book in the middle. And if a student is reading a book, the student must finish the book completely. It should not happen that 10 pages of this book are read by this student and 10 pages are read by some other student, right? It should not happen this way. So with these constraints, we need to find out minimum possible value of the maximum pages read by a student. We have already discussed the recursive solution, and we have also discussed a dynamic programming based solution in the dynamic programming track. Here we are going to talk about binary search based solution. The binary search based solution that we are going to use here is going to work this way. See, the maximum pages assigned to a student is upper bounded by total number of pages, right? In the worst case, a student will read all the pages. For example, if you have k equal to 1 only, right? So that's value 70 here. We have total number of pages to be read is 70. And what will be the minimum possible answer? See, in answer, we need to find out minimum value of all maximum pages, right? And a student who is reading the book 30, right, a book with pages 30, has to finish this book, right? So the minimum possible value for this answer is 30, right? Our answer cannot be less than 30. In other words, our answer cannot be less than maximum pages in a book. So that's the range that we have for answer. Our answer must lie between 30 and 70. Now what we are going to do here is, we are going to do binary search in this range. And we are going to first try with answer 50. We are going to check if 50 is an answer or not, 50 is a feasible solution or not. How do we check if 50 is a feasible solution or not? We are going to find out number of students required such that no student reads more than 50 pages, right? If 50 is an answer, then no student should read more than 50 pages. So we try to figure out how many students are required for 50 pages maximum. So if we assign this book to student 1, less than 50 can be assigned. This book can also be assigned, total is less than 50. This book can also be assigned. So all these 3 books can be read by one student, but we cannot assign this book also to the same student, because in that case the total will become 70, which is more than 50. So these 3 books are assigned to student 1, and the student 2 reads the book 30. We need one more student, right? And student 2 can read the 30 page book, and we are done, right? We don't need any more student. So our answer is turning out to be 2 students required for 50 as a limit, right? Which is less than or equal to k. So 50 is a feasible solution, but we want to find out the minimum value, right? So what are we going to do? We are going to skip the right side of 50, because if 50 is an answer, then 50 is a feasible solution. Then 51, 52 up to 70, all these will also be feasible solutions, right? And we have found an upper bound as on the answer as 50, and our answer will now be either 50 or less than 50, and we want to find out minimum possible value of this answer, right? So we are going to search in the left half. We are going to search from 30 to 49. Now we reduce our range to 30 to 49, and we take the midpoint of this range also for binary search, and we get the midpoint as 39. Now we check whether 39 is a feasible solution or not. How do we check? We assign 10 to the first student is less than 39. We also assign 20 less than 39. Now we cannot assign 10 to the same student, because then it will become more than 39. So we are going to need a more student. So student 1, student 2. Now if I assign 30 to the same student, it will be 30 plus 10, 40. So I need one more student. 3 students are required now. And this count is more than k, right? K is 2. So this is not a feasible solution. So what should we do in this case? See, if 39 is not a feasible solution, then any value from 30 to 39 is also not going to be feasible solution. 38 is also not going to be feasible solution. So what we do in this case, we go to the right half. When we go to the right half, we change our range from 40 to 49. We again compute the midpoint and we get the midpoint as 44. Now we check if 44 is a feasible solution or not. So 44 is a feasible solution. You can check it by linearly scanning through the array. This one student gets 40 and the next students get 30. So we update our result to 44. See, I am updating the result in every feasible solution because we are approaching toward minimum, and last value that we get, last feasible solution that we get is going to be our final result. So we just need to update the result variable whenever we see a feasible solution. Now 44 is a feasible solution, so there can be a feasible solution smaller than this also. So we go to the left half, we change our range from 40 to 43. We again find the midpoint as 41 and we see 41 is a feasible solution. Since 41 is a feasible solution, we again go to the left half and we change our range from 40 to 40. And this time our midpoint turns out to be 40, and 40 is also a feasible solution. Right, we can always check whether a solution is feasible or not by scanning from left to right, and we increment the number of students when we have the current sum more than the sum required, and we reset the current sum, right? That's a simple way of checking. So 40 is a valid solution. We need one student here and one student here. Now our range is reduced to one element, and according to the logic, if we go to the left of this, left and right or low and high, they will cross each other, right? So our binary search will stop, and at the end we'll return 40 as an answer. So you have complete idea now. Please pause this video and write down the solution yourself. Here is implementation of the idea. This is implemented close to C++, and with minor changes it can become a Java code as well. For example, we don't need to pass size of the array in Java, we can get it using arr.length, and instead of bool we need to use boolean in Java. And here also, instead of simply using max, we can use math.max in Java. Apart from these minor changes, the code is same in both C++ and Java. So what are we doing here? We are first computing the sum and maximum value in the array, right? So if you take this example, your sum is going to be 35, 10 plus 5 plus 20, and maximum value is going to be 20. So that's what we do here. We find the sum of elements and find the maximum value. We initialize max as 0 and sum also as 0. Now we are doing the binary search in the range from max to sum, right? So low is max and high is sum. And we are simply doing the binary search. We are computing the midpoint, and then we are checking if the midpoint is a feasible solution or not. So if you see this example, the midpoint turns out to be 27. We check if it is a feasible solution or not. And this is a function that checks for feasibility. And how does it work? It takes an answer as an input. We are passing mid here, which is taken as an answer. Takes ARR, N and K. And what this function does, it simply traverses through the given array and checks how many students are required when no student gets more than 27 pages to read. And how does it find out the required students? It simply traverses through this array, right? So initializes the current sum as 0, then traverses through the array, and for every element ARRI, it checks whether we can include ARRI to the current sum or not. If we can include it, we include it and update the current sum. And after including it, if sum becomes more than the answer which is provided to us, then we need to increment the required students and we need to begin with a new student. So sum for a new student becomes ARRI and number of required students increments by 1. And at the end, if the required students are less than or equal to k, then we return true, otherwise we return false. That's the simple feasibility check. So after checking for 27's feasibility, we update the answer as 27 because it's a feasible solution. So we get our answer or result as 27 and we go to the left half because there might be a lower answer also. We need to find out the minimum possible feasible solution, right? This is one feasible solution. So to go to the left half, we change our range from 20 to 26 and becomes now mid minus 1, and then we get 23. Now we again check whether 23 is a feasible solution or not here. 23 turns out to be a feasible solution because you assign 15 to one and 20 to the other. So you again go to the left half, you change your range from 20 to 22 and you get the midpoint is 21. 21 is also a feasible solution. So you go from 20 to 20 and you get the midpoint as 20. You update your result as 20. We are updating the result every time we see a feasible solution. Now our midpoint is 20 and low is also 20. We are going to change our end to 20 minus 1, 90. And next iteration would not run because low is not smaller than or equal to high. High now becomes 19, which is smaller than 20. So we do not proceed further, and at the end we return our result as 20. So this is how the solution works. Now what is the time complexity of this? See, we are doing a binary search in the range from max to sum. So we are going to do log sum minus max work, right? And for every iteration of this loop, we are calling a function is feasible, which is a theta n function. So we are going to do big O of n into this much work. So I'm using big O because this binary search may stop before doing all the log iterations. So that's the time complexity, and if I try to get an upper bound, I can also write the upper bound as log sum. Right, I can ignore the max because I'm using upper bound, right? So that's also a feasible upper bound for time complexity of the solution. So this solution would be better if your sum is not very high. Otherwise, you can use dynamic programming solution, which can work in big O of n square k time.